I call this presentation the need for speed. We've been learning about motion, and we've done some calculations of speed and velocity. So, do you like to go fast in real life? Well, I'd like to take a look at some of the consequences of going fast in your vehicles. Do you drive yet? Many of my students are about to learn or have just recently learned how to drive. So most are relatively inexperienced drivers. Now, driving is a huge responsibility. You're driving a 3,000 or 4,000 pound missile, and you could do some damage with it. Not only is your life at risk, but so is the lives of other people. So let me just start out by saying, please, when you're driving, drive responsibly. Wear a seat belt and make sure everybody else in your car is wearing a seat belt. Put your phone down, anything else that might be distracting you. Don't drive after you've been drinking or using illegal substances, or even if they're legal substances. Some cold medicines or prescription medicines specifically say you probably ought not to drive after taking this medication. And follow the rules of the road. When you see a stop sign or a red light, that means stop. But what I want to focus on in particular for this particular presentation is obeying the speed limit. There are posted speed limits. Those are laws. So let's look at why you should pay attention to them. I have personally observed many teenagers driving too fast. And I see this in my own neighborhood. And as an experienced driver, it really scares me because I know that the faster you're going, the less time you have to react if something unexpected occurs, and the more space or distance it's going to require for you to come to a stop. Now, I'm not trying to pick on teenagers too much. Adults of all ages drive too fast and too aggressively. So if everybody does it, what is the big deal? Well, I want to make basically two main points. One, people speed a lot of times, they say, because they want to get somewhere faster. So if you arrive safely, I want to show you by using the speed formula we just recently learned that you probably only saved a few seconds of time by speeding. While at the same time, number two, you greatly increased your chances of getting hurt or hurting somebody else, damaging your vehicle or damaging other people's property. So let's get started by looking at the physics behind speeding. You probably think that going faster will save you a lot of time, that you'll get to your destination much sooner. But I want to calculate exactly how much time you would save by looking at the speed formula that we've learned in class. If you look at a total trip, the average speed for that trip equals the total distance divided by the total time. So for example, if you went an average speed of 60 miles per hour, miles is distance, hour is time. We could convert that to other units, such as minutes. An hour has 60 minutes, so 60 miles per hour is the same as 60 miles per 60 minutes. If you divide out the 60s, then you get that 60 miles per hour is equivalent to 1 mile per minute. If you think about that in reverse, what we just said is that to go 1 mile requires 60 seconds if you are traveling at 60 miles an hour. Let's keep that timeline in mind, 60 seconds to go 1 mile. If we use 1 mile as our distance for a given trip, how long would it take us to go that mile if we're traveling at an average of 65 miles per hour? Well, first you should recall that we can put the speed formula into a magic math equation triangle. it looked something like this. So if we want to calculate time, basically if you just think of yourself as putting your finger over the T, what's left? D over V. So our formula is time equals distance over speed. Now let's plug in the numbers that we have. We have V equals 65 miles per hour and D equals 1 mile. So 1 mile divided by 65 miles per hour equals 0.0154 hours. That's how long it would take to go 1 mile at 65 miles per hour. But who knows what 0.015 hours are? Let's figure that part out next. You can do something called a conversion. First, we'll convert to minutes. 0.0154 hours times the conversion factor of 60 minutes per hour. Lets the hours cancel out top and bottom of the fraction, leaving us with 0.92 minutes. You may notice, by the way, that I'm being a little bit fast and loose with significant figures here because we're dealing with made up numbers, not actual measurements. So I'm going to keep it to 2 or 3 significant figures in our calculations. 0.92, or actually 0.923 if I include another significant figure, minutes. How long is that? Well, a little bit less than a minute, but let's figure out exactly how long that is in seconds. So let's do another conversion. 0.923 minutes times the conversion factor of 60 seconds per 1 minute allows the minutes to cancel out and gives us 55.4 seconds. Now remember, to go 1 mile at 60 miles per hour required 60 seconds. Now we're saying if we increase our average speed to 65, we can cut that time down to 55.4 seconds to travel 1 mile. That's a whopping 4.6 seconds that we just saved. We got there less than 5 seconds faster by going 5 miles per hour faster. Let's speed up a little bit more. What if you went an average of 70 miles per hour on your 1 mile trip? Now how much time would you save? Well, let's solve it in a slightly different way just to show you that there's not just one pathway that you have to follow in order to solve physics problems. I want to convert the speed to miles per second before I plug it into my time equation. So what I do is I multiply by the same 2 conversion factors as I did in the previous problem. I can do them both at once. So the miles per hour times hours per minute, now I'll have hours on top and bottom, those will cancel out. The minutes on top and bottom will also cancel out. The units I have left are miles per second. I have 70 times 1 times 1 on top, 1 times 60 times 60 on bottom. That's 70 divided by 3600. That equals 0.0194 miles per second. So 70 miles an hour is the same as 0.0194 miles per second. Let's use that for our V in our time equation. Plug in the numbers, and you'll see that 1 mile divided by 0.0194 miles per second, the miles on top and bottom cancel. It leaves you with 1 over seconds, which you can trust me flips up and becomes just plain old seconds. So at 70 miles an hour, you can go 1 mile in 51.4 seconds. In other words, compared to 60 miles an hour, you can get there a little bit less than 9 seconds faster. You save 9 seconds of time. But compared to 65 miles an hour, on average, you only saved 4 seconds. 4 seconds of time. That's all you got by going 70 miles an hour. Now, Kentucky's rule speed limit on freeways is 70 miles per hour. Let's just go faster than that. Let's break the speed limit. So at 75 miles an hour, you can go 1 mile every 48 seconds if you did the calculations. In other words, that's a whopping 3.4 seconds of time less than if you went just the speed limit. 7.4 seconds less than 65, or 12 seconds less than 60 miles an hour. In other words, by going 75 miles an hour, if you go 1 mile, you just save 12 seconds of time. 12 seconds. That really doesn't seem like a lot of time to me. So wait just a second now, Dr. Kemp, are you telling me that if you and me had a race, and you, Dr. Kemp, went 60 miles an hour, and I, student, went 75 miles an hour, that I would beat you by only 12 seconds? I've been talking longer than 12 seconds just to read you that paragraph off the slide. That's how much time you saved. It doesn't seem like a lot, does it? And that assumes an average speed. If you know anything about real life driving, then you know if you start, you're not going 60 or 75 instantly. It takes you a little while to get up to that speed. And then you have to come to a stop. So if the trip really is only 1 mile long from start to finish, then you're going to save less time than 12 seconds. Or you're going to have to go much faster than 75 in the middle of it in order to get the average up to 75. Now you're saying to yourself, well, that was just for 1 mile trip. Most trips are longer than 1 mile. Wouldn't I save a lot of time if I went further? Well, let's look at that. Let's pretend like there are 4 people and they're all going to take a 10-mile trip to school. They all leave at the same time. How much faster, how much sooner does a fast driver arrive? I'll construct a little table here and let's take a look. Let's say driver A goes 60 miles an hour, B 65, C 70, and D 75 miles an hour. Now driver A going 60 miles an hour goes a mile a minute, and so to go 10 miles requires 10 minutes, which is 600 seconds. How much time will driver B save in that 10 miles? Well, it requires 554 seconds, so they save less than a minute, 46 seconds. How about driver C? 514 seconds to get to school. That's 86 seconds, less than a minute and a half. Driver D, going really fast, 75 miles an hour, gets to school in a whopping 120 seconds faster. Woohoo! Wow, 120 seconds. But wait, that's only 2 minutes. Drove 15 miles an hour faster. You exceeded the speed limit. And that's an average speed. And you got here 2 minutes. To get to school 2 minutes or sooner, you increased your chances of killing somebody by 10%, maybe yourself. And that's not to mention your chance of getting a speeding ticket, higher insurance rates for years to come, and maybe getting sued by somebody because you hurt them in a car accident. 2 minutes. Is it worth it? Really? You have to keep in mind that the results we just talked about are assuming average speeds. In other words, that's got to include starting and stopping. Realistically speaking, you would not arrive 2 minutes sooner because of all the what I call great equalizers around here, red lights and traffic jams. If you arrive sooner than the others, it's a lot more likely that it's because there was a red light that held them up, not that you went so much faster that you got here so much sooner. The chances are very good that if you tried to increase your average speed by 15 miles an hour from 60 to 75, that you really would not arrive 2 minutes earlier. You might arrive a few seconds earlier than the other drivers, but it would probably, almost certainly be less than a minute earlier. And again, it's probably not even your speed that counted the most. It's how many red lights did you get held up at versus them. And I'm not telling you to run red lights. I want you to stop at those red lights. That's what the red means. Now consider this. I was pretending like there were 4 different drivers, but what if we're talking about the same driver? What if we're talking about you making the same trip every day at different speeds? What I'm trying to explain to you is you will not get here with any significant time difference. It doesn't have to be to school. Whatever your destination is, you will not get there very much sooner by speeding up way above the speed limit. Again, I got to remind you, we're talking average speeds. If you wanted to go an average of 75 miles an hour and you've included starting and stopping, then you're going to have to be going 85, 90 miles an hour in the middle of there. That's way too fast. You have a very much increased chance of causing damage to you or somebody else's vehicle, the property, or causing harm to yourself or to others, especially when the driving conditions are not ideal. In other words, when there's a lot of traffic on the road, when there's fog, when there's rain or any sort of precipitation, when it's dark. Let's just go back and just say that we went 60 miles an hour on average and 75 miles on average over the course of 1 mile. You just saved 12 seconds of time. But do you know, research has shown you just increased your chance of having an accident by 5%. That's a pretty big jump. You increased your chance of getting hurt in an accident by 7.5%. And you increased your chance, if you did have a serious accident, of being killed or killing somebody else by 10%. Just so you could save a few seconds of time. Now, lots of people say, yeah, I go a little too fast, maybe a few miles over the posted speed limit. And so that's not really a very big deal. It's an acceptable risk. And we see other people do it. But one of the points that I'd like to make to you is that you're not other people. You're not in their car. You don't know whether or not they're a better driver than you. Maybe they have a better vehicle than you. Maybe they have better tires than you. Tires that have more friction, more grip on the road than yours do. So just because somebody else goes around a curve at 60 miles an hour does not mean that you can. And when people go, say, only a few miles over the posted speed limit, they think that the worst that's going to happen to them is they might get a speeding ticket. But what I want to show you is that going just a little bit faster can actually have quite severe consequences. Let's do a little thought experiment. Imagine you're on top of a 12-story building. You're 120 feet above ground level. You look down and you see all the little people walking around down there. Now, let's imagine that's like a parking deck, and you just get in your car and drive right off the side of that building. Wait, what? Who would do that? That wouldn't be safe. Well, if you do the math, something we'll calculate later on in this class, you would see that when you hit the ground after falling 12 stories, you'd be going 60 miles an hour. So in other words, the force of impact when you hit the ground in your car there is the same as if you were on level ground going at 60 miles an hour. That's physics. I'm not trying to scare you from driving 60 miles an hour, 65, 70 miles an hour. What I'm trying to do is just get you to understand that physics is at work when you're driving. It's at work not only on your car, but on you as well. And your body is not designed to cope with high-speed impacts. So you've got to be careful. A lot of people go really fast these days because our cars are really good and they're capable of high speeds. But a lot of people think that the safety features, things like seat belts and airbags, side impact zones and crumple zones on the car, they think that those things are going to save them if they were to have an accident. Indeed, safety features like airbags and safety belts have cut down on the number of fatal accidents during my lifetime. Let me show you a graphic to show you what I mean. If you look at the red line on this graph, this is the number of deaths caused by traffic accidents. And you can see it starts way back in the early 1900s. And it goes up pretty high. By the early 1970s, we're talking over 50,000 people per year in this country were being killed in traffic accidents. Now that rate is on its way down. It's not a 100% smooth slide, but it's definitely on its way down. And that's due in large part to the vehicle safety features that have been added on cars since I was a child. I was born in 1960. Okay, we didn't have seat belts, and if we did have seat belts, we usually had too many kids in the car to wear them anyway. There were no airbags. There were no side crumple zones or front crumple zones. There was no side beams to protect us. So yeah, if you got in a wreck, especially at a high speed, you're in a lot of trouble. If you look at the blue and green dotted lines, those show a more steady trend. What that is if you're looking at the blue is per 100 million vehicle miles driven, or the green is per 10,000 motor vehicles. In other words, there are a lot more cars on the road today than there used to be. But even though there's more cars, they are getting safer. So having safer cars and better roads has cut down on the chances of you being seriously injured or killed in a car accident. It has not totally eliminated those chances. Consider, for example, that the faster you're going, the less those safety features are actually effective. There's an inverse relationship. But even more importantly, just because your car has safety features doesn't mean that your body has changed in any significant way. Physics still applies. In particular, I'm thinking about a property known as inertia. We'll talk about this a little bit later in the course, just in a few days actually. Basically, the implication that your body has inertia is that you might still get hurt even if your car survives. I'm thinking about here that you have probably seen lots of movies where people were in not just car accidents, but let's say like Iron Man. You know, Iron Man puts on a super suit and runs into a wall. And it's okay because the suit protects him. Well, I'm sorry to tell you, but the suit would not protect him. He would be hurt if he ran into a wall, no matter how strong his suit is. So that's just physics at work, and you need to learn about that, and we will talk about that during this course. It's amazing the psychology behind risk-taking. A lot of people get behind the wheel and they just think, well, it's not going to happen to me. People just don't take into consideration the fact that when you're going faster, you can't steer around things that might be obstructions in the roadway or running out in front of you. You can't steer around them anywhere near as well as you could if you're going just a little bit slower. And if you hit the brakes and you're going faster, it takes a significantly longer distance to come to a stop. We'll do some calculations about that in a later unit. We'll talk more about force and acceleration and kinetic energy and stopping distance and so forth later on in the course. Just to give you a preview, think about this. If you're in your car and you hit something and you're going 25 miles an hour, that's going to mess your car up pretty bad. It may not kill you or hurt you, but your car is going to be a wreck. Now, let's say you hit that same thing and you're going 35 miles an hour. How much worse could it be? You're only going 10 miles an hour faster. That's about 40% faster than what you were going at 25 miles an hour. But you would hit that object with almost twice the amount of kinetic energy. You're going to do twice as much damage. The force of a collision increases in proportion to the square of the speed. That's one of the things we'll take a look at in a later unit. So if you're going 50 miles an hour versus 25 miles an hour, that's 4 times as much kinetic energy At 75 miles an hour versus 25, that's 9 times the force of impact, or the amount of energy that's released in that impact. So physics is important to learn so that you can avoid situations like this. Let me just wrap up this presentation by focusing on money. Going the speed limit will save you money. First, you can avoid getting traffic tickets, avoid getting higher insurance costs. That's obvious. As I've mentioned several times, going at higher speeds results in a higher likelihood of you being in a wreck, which is going to cost you money. I mean, even if you just get in a fender bender, I don't know about you, but my deductible is $1,000. That means I have to pay $1,000 before my insurance will pay even a penny. I also would have to take off time out of work in order to take my car to the shop or go pick it up. And if I hurt somebody else, I might get sued and have to pay their doctor bills. And here's something else to consider on the other side of it. The faster you go, the more gasoline your car consumes. If you slow down, you will save gas. At about 45 to 50 miles an hour, the average light-duty truck or car in this country reaches its maximum fuel efficiency. So according to the government, if you go 5 miles an hour faster than your maximum fuel efficiency, so let's say about 50 miles an hour, for every 5 miles an hour you drive faster, that's going to cost you about 15 cents per gallon. So by the time, if you're going 75 miles an hour, that's going to cost you nearly 50% more in fuel. If you're going on a long trip, that's a lot of money. But even if you go on short trips, but you do it a lot of times, that's a lot of money. Slow down. It will save you some money. The bottom line is, I want you to drive safely at a safe speed. It is not worth risking the rest of your life to save a few seconds of your time right now. If you're running late, just be late and accept the consequences, because they're probably going to be a lot lower risk than the risk that you're going to take by driving faster. You're not going to get there much sooner. Slow down, drive safely, learn from physics. It has a lot to teach you.